Hello students. In the previous lecture we discussed about the introduction of steady magnetic field uh, and also we have discussed about Biot-Savart's law statement and its applications, and also we have discussed about the Biot-Savart's law statement. Now we will discuss about the application of the Ampere circuit law. So that is what is the application of the Ampere circuit law is finding the total current enclosed by the closed path, right? So to find out this application of Ampere's circuit law, we consider the coaxial transmission line. So you can see in this slide there is a coaxial transmission line where we are considering an example for the Ampere circuit law application. So in coaxial line we have two concentric solid conductors that carry equal and opposite currents. This plus I and minus I. So inside conductor it will carry plus I current and outside conductor it will carry minus I current, and inside conductor is having a radius R is equal to A and outside conductor is having a radius of B as well as C, right? So now the line whatever it is along z axis is assumed to be infinitely long, and circular symmetry suggests that H will be entirely phi directed, means H is along the phi direction and it will vary only with the radius rho, right? Because as it is a phi direction, so our value of H will be varied along with only a radius rho, right? Our objective is to find out the magnetic field for all the rho values whatever we get in this uh, surface, that is what with the radius all the values of rho, right? So this surface is considered. Now next we go to the field between the conductors. So obviously as there is a two conductors, there exists a field between the two conductors. So I told about inner conductor. So inner conductor can be thought and of made up of bundle of filament currents. So bundle of filament currents. So inner conductor is made up of bundle of filament current, each of which produces a field along the long wire. So as this inner conductor is placed along z axis, so it will produce the field along the long wire, right? Now for an example we consider the two such filaments on the inner conductors located at the same radius from z axis, that is rho 1, right? But which lie at the symmetry phi coordinates. So these will lie at the symmetry of a phi coordinates, therefore those symmetries are phi and minus phi 1. So their field contributions superpose. If the field contribution whatever we got by these two filaments superpose and give a net H phi component as shown. So it will give a net H phi component as shown. The same happens for every pair if I symmetrically located filaments which taken as a whole make up the entire center conductor, right? So therefore whatever the field developed by the inner conductor is there, it will be considered as taken as whole and make up the entire center conductor. So the field between the conductor is thus found to be same as that of filament conductor on the z axis that carries the current I. So you can see in the figure here. So rho is equal to rho 1 and phi is equal to minus phi 1, rho is equal to rho 1 and phi is equal to phi 1, and the current and the direction of H is only H phi only. So you can also see in the figure, one more figure is there below where H phi is in between the conductor. It is the field between the radius A and radius B. So we want to find out the field between these two conductors of radius A and radius B, that is rho is greater than A or rho is less than B. So as this H phi is need to be calculated as it is nothing but a current in the inner conductor So therefore we will get the equation as h phi is equal to I divided by 2 pi rho, where rho is nothing but lying which is greater than A and which is less than B. So this is the field between the conductor, that is h phi is equal to I by 2 pi rho. Okay, so next we go to the field within inner conductor, right? Field within inner conductor, you can observe in the diagram. So there are two conductors. One is inner conductor with a radius A, outer conductor with a radius B. So field you can see in the figure with a blue line, it is inside the conductor. Okay, so the current is uniformly distributed here, so H can be assumed circular everywhere. So inside the inner conductor at a radius rho, we again have integration of H dot dl is equal to nothing but what, we have a radius of 0 to 2 pi, right? So H is h phi and dl is nothing but what, rho d phi. So therefore after integration what we get is h phi 2 pi rho, right? But as the current enclosed, but now the current enclosed is, we can get a current enclosed in this inner conductor is current I enclosed is equal to I into rho square by a square. So therefore, so that 2 pi rho h phi, as already we have got by applying Ampere circuit law, is nothing but equal to I rho square divided by a square. So finally h phi is equal to I rho divided by 2 pi a square, that is nothing but rho is less than A. So this is nothing but field which is available within the inner conductor, that is h phi is equal to I rho 2 pi a square, right? Now next, field outside both conductors. So as you can see in the diagram, so there is a radius A, radius B or C, and a field I am going to be placed outside the conductor. So outside the transmission lines means rho is equal to rho is greater than C. There is no current enclosed by the integration path. So therefore for this case the integration over closed surface h dot dl will be 0. So as the current is uniformly distributed and since we have a circular symmetry, the field would have to be constant over the circular integration path, and so it must be true that h phi will be 0. So h phi is 0 where when we have rho is greater than C. So you can observe in the figure their magnetic field which is more than radius C, it is considered to be as an 0. The current enclosed will be 0, also the h phi will be 0, right? Next we go to the field inside the outer conductor. So you can see here, now as in the previous case, field is available inside the outer conductor. So outer conductor is having a two diameters. Outer conductor will having inner diameter and also it is having outer diameter. So inner diameter is radius is B and outer diameter radius is C. So in between that you are having the field developed in between the B and C. So therefore inside the outer conductor the enclosed current consists of that within the inner conductor plus that portion of outer conductor current existing at the radii less than P. Means whatever the current enclosed by B and C are considered here, total current of inside conductor minus the current due to B and C. So therefore after applying the Ampere circuit law becomes, so already we know that current enclosed nothing but 2 pi rho h phi is nothing but equal to I minus I into bracket rho square minus B square divided by C square minus B square. Okay, so if you subtract total current, that is if you subtract the current due to B and C from total current, we get the 2 pi rho h phi. So finally h phi is nothing but equal to I divided by 2 pi rho C square minus rho square C square divided by C square minus B square. So this is a field available inside the outer conductor. So that is a rho, whenever we have a rho is greater than B or rho is less than B. Okay, you can also see in the diagram. So that is what field inside the outer conductor, right? Now next we go to the what is the strength of this magnetic field as a function, because as it is what function of a radius in coaxial line. So you can see, observe in the figure, that is a graph. So whenever you have a radius a, you have a maximum of I by 2 pi a, right? Whenever you have a radius 2a, you have a what magnetic field intensity is I by 4 pi a. And as whenever you have a radius of 3a, that is nothing but equal to b, your magnetic field intensity will be decreased. And whenever you have a radius of 4a, that is equal to c, that is magnetic field will becomes 0 on the surface. So combining the previous result and assigning the dimensions as shown in the inside below, we find this magnetic field strength as a function of a radius in the coaxial cable. Means the magnetic field will depend on the value of the radius. So as per the graph you can see here, so as you can have what radius is equal to a, radius can be 2a, radius can be 3a, or radius can be 4a. Based on that you will get a value of magnetic field intensity, that is I by 2 pi a, or I can get I by 4 pi a for radius 2a, like that you can get. So as radius will be decrease, and the magnetic field intensity will be decrease, right? So this is about the one of the application of coaxial transmission line, that is the application of ampere circuit law. Okay, so remaining some of the section will discuss in the next video.